We're going to run just the x64 debug build, and I'm going to show you some things. Now, as you know, as you get closer to a game launching, you start thinking about what are the platforms it's going to launch on, and how do we run well on the lower end platforms that can't do as much graphically and can't do as much CPU wise? And like, hey, I did all these things to get the game working, where I kind of swept some stuff under the rug, and like, maybe it's time to take care of those things that I swept under the rug, right? So one such thing, I think we're rebuilding shaders because we did a lot of shader work. All right, go to the overworlds. One such thing is that when I wrote a lot of the gameplay code initially, this gameplay code is about getting these different universes with different rules to like all interoperate, right? And sometimes it was very challenging. There was some stuff I had to rewrite like 5 times in the beginning or whatever, not an exaggeration. So, and in the process of writing this code, I didn't know what was going to be the best way to represent things and all this. And so, um, sometimes you write code that's very easy and lazy. So, for example, if you think you're going to have one screen levels with just a tiny amount of puzzle stuff and like 10 manipulable entities, like I thought this entire game was going to be for the history of the game, then you'll write a lot of like n squared for loops and things that search all over for stuff. Because you're like, hey, A, I'm just prototyping the game, but B, maybe this will never need to be faster anyway, right? And then, you know, oh, what just happened? I was trying to show the overhead map, but it doesn't work anymore. All right, now it's working. Anyway, we can unfog and show the whole map. So like, there's actually a lot of stuff on this level, and there's more stuff than you can see here. So in terms of interactive entities, there's about 7,000 or 8,000 of them. And why are there so many? It's like sometimes we have barriers made out of rocks and stuff, and those are regular gameplay rocks, and they add up, and like all the little level entries count, and all these things. So it's time to pay the piper on some of this stuff before the game comes out, right? Now, when we go on to lower end platforms such as the Gabe deck, or one presumes the Nintendo Switch, or this laptop, which is a ThinkPad X1 Carbon, right? These are all lower end systems with lower end GPUs and also lower end CPUs. And it turns out that the CPUs are slow enough that some of the gameplay code that I wrote on such a big overworld where it was not intended to run becomes very slow. And it's extra slow in debug build because it has all these asserts. And so you're gonna see it worse. So the thing is, there's stuff happening off this screen that you can't see where objects are moving. And every time those move, we call this function called post move reevaluate. And that does a bunch of stuff. And so you see our profile here is very noisy. There's these giant spikes every time we call post move reevaluate. Now, we'll look at this function in a minute because it's instructive. But post move reevaluate, I was like, why is this slow? And it's broken up into a bunch of sections. All right. And the most expensive of these is section 5B. All right. Then there's section 4 and all these things. And in this view, you can see when I go on section 5B, these giant spikes in the graph light up that go off the top of the graph. That's our slow thing, right? So where is 5B? Well, it's called from 5A, which is called from 5, which is called from post move reevaluate, which is taking 13 milliseconds per frame. This isn't debug build again, right? But it's good for your debug build to go fast, right? So 13 milliseconds per frame that's very bad, right? That would mean, um, if you're going at 60 FPS, um, which is not considered a high frame rate on PCs in 2025, if you're going at 60 FPS, right, you have, what is it, 33 milliseconds? 120 FPS, you have 17 milliseconds for the whole frame. So 13 milliseconds for one function that isn't even doing anything interesting and that's being called in a spiky way, that's really bad. Now, again, it's not actually this slow because this is a debug build, right? On this PC, the release build runs pretty fast. It's like less than 1 millisecond, but 1 millisecond is still a long time on video games. And again, running debug build on a fast machine is a good way to sort of simulate like what if your machine was slower. It's not apples to apples, but as a first approximation in terms of telling you what are the big fatty things that you need to attack, that is what it is. What is the reason to go beyond 60 FPS? Oh my God. Oh my God. All right. So that's the goal. I have a goal of making this function faster, but we can't get to it yet today. I'll explain why. All right, let's go look at the function. So let's go. Okay, here's post move reevaluate. This is a bunch of stuff that we call, it's a turn-based puzzle game essentially, although some turns are timed, right? So it's kind of real time, kind of turn-based. And every time a turn ends, we run this code, and it's not at first glance that much code. It's only 230 lines, but it calls a bunch of other functions that do a bunch of other stuff. So here's the infamous section 5 that was the slowest part. And section 5 is figuring out when things should fall. And because I wrote this code very early on, because, if you're making a game, you got to know when stuff's going to fall, like really early in development, right? So this code has been here forever. And what do we do when we're going to see if something falls? Well, we look at every entity in the world and we ask, is there something under this entity supporting it, right? Still. And if not, it should fall. And as you can imagine, when there are 8,000 movable entities, you don't really want to do that anymore, right? And for each one of these, we do stuff like iterate over all the active transactions to see if it's in there, right? This stuff is about actually creating a falling move for things. So this almost never happens, but so this 5B, we sort all the things, all the thousands and thousands of things on the overworld, and then blah, blah, blah. Okay. So now, where there was a specific thing that I wanted to look for. I'm trying to remember what was the function. Oh yeah. So, okay. There's a different thing that also takes a lot of space. So section 4, let's see where that was. Section 4 is also non-negligible. The reason I was looking at it is, so again, debug build is not exactly a good approximation. And if you look at the release build, section 5 and 4 are a little closer. It's still like section 5 is super expensive and section 4 is less expensive, but the ratio is a little closer than this, right? So, okay, what's section 4 here? It's figuring out if guys should get crushed by stuff that's on them or monsters, right? And it's like, why is that taking a millisecond per frame, even in debug build? And the reason is, because for every monster, we're calling this is a prime example of just like what happens in programming. All right, for every monster, when we start writing this game, we're like, oh, there's not going to be that many monsters on a level. What, 10? Well, on this level, there's like hundreds. All right. So first of all, there's like hundreds. And then we call weigh single stack because if there's too much weight and the monster's not very strong, the monster gets crushed. All right. So what is weigh single stack? It sounds simple, right? Whoops, I spelled it wrong. It sounds simple. So collect full support stack. That just tells us everything that's on top of this entity. And then, weigh the single entities and add up that weight, and that's the total weight. All right. So now what is collect full support stack? Well, here's the thing. The way your data structures are set up is very important, right? So if you could just query a data structure that says who's on top of me, then you would just follow that up like a linked list. Everyone who went to computer school knows what a linked list is. It might not quite be that simple because maybe there's some weird pathological cases in which more than one thing is on top of you. Even in a game like this, that's a grid-based game, that's actually possible in some very rare cases. And I don't mean more than one thing at a stack, but more than one thing at one level. So it's a little more like a tree. It's almost never a tree, but in very rare cases, it's a tree. Okay, so if you have that data structure, it's very fast, but we don't have that data structure. And it wasn't clear to me early on whether we were going to have that data structure or whether we would need it. In fact, I thought we wouldn't. So what do? For every entity, every monster, which I've already said there are hundreds of monsters, right? After every move ends, we go and see how much weight is on the monsters. And how do we do that? Well, we go over every gameplay entity in the world and we ask if that entity is standing on the monster, right? Who is that entity supported by? Is it the monster? Okay, this is actually, this probably shouldn't be true. This shouldn't, you probably should weigh on him if it's by teleport, but whatever. The point being, we do that, and then we add it to the list, the array. Okay? So for let's say it's 300 monsters. I don't know how many it is. We could find out in a minute. Let's find out. It'll take a second to load again because debug build monster, select all. Okay, it's only 140 monsters. No problem. So for 140 monsters, we iterate over 8,000 gameplay entities. Maybe it's 12,000. Let's call it 8,000. So let's just say it's 100 monsters, just to round it down. So 8,000 times 100 is 800,000 iterations, and then you round it up for the 40. It's a million, 1.1 million steps through this loop every time you move in the game. And it's merely one of the things that's happening, right? So when people ask, why is software so slow? It's stuff like this. Matt's asking, is the game CPU bound on most machines? Not on most machines. On Steam Deck, it is a little bit. But the thing is, it's spiky is the point, right? So all this stuff happens when a move ends, and there are timed moves. And so if your frame rate is spiky like that, that's really unpleasant. You don't notice it right now on a desktop PC, but you do notice it on Steam Deck, okay? And you probably will notice it on Switch too and all this stuff, right? So all of this is just to say that I have this goal in the short term, like this week. I want to rewrite this code, right? What do I want to do? I have a data structure that goes the other direction, right? And it's probably one to many. Although, when I was saying it could be like a tree, I was thinking of supported via teleport. So maybe if we don't do that, it really could only be one to one. But just in case, it's a 1 to n where n is small data structure where anytime we say, who am I supporting, that could be a fast query. And then there's other things we would do too to make it faster. Like instead of searching every monster in the world, only search monsters who moved or who had something move on top of them, right? Um, what's wrong with that? So, uh, so that's two directions in which we can make this faster. And by the time we do both of those things, it should be plenty fast on all machines, even if it's not the most optimal code. Okay. How do you do this responsibly? Back in the early days, when I was just getting into games in the 1990s, I would have just been like, fuck it, I'm going to write a new data structure. And it wouldn't have worked very well. It would have had all these weird bugs that would have taken a while to debug, and the game would have been kind of broken. And I wouldn't have known that because I wouldn't have tests and all that. All right. So now we have tests for the game that run through every level. In theory, we'll get to that in a minute. We have tests that run through every level and replay all the levels. And so you can write some code that validates that your new code gives the same result as the old code, right? So here's what I could do. When I call collect new support or collect full support stack, what I can do is I can fork this function off. I can call this one collect full support stack old. Pay attention, this is a super good uh, software engineering technique. This is like one of the amazing things that you learn to do. All right, so we can say old result is the old version of this, right? And then we write a new function that uses my data structure and all that. And we say, collect full support stack new. And then we say, assert arrays are the same or whatever, right? This just asserts they're the same length and then asserts all the members are the same. It's not quite an array compare because it would be legal for the order to be different, right? But so you do this and then you return new result, right? And then you run your tests over all your levels and you verify that this returns the same result for your old algorithm and your new algorithm. It probably won't in the beginning, maybe because your new algorithm has bugs and that helps you catch the bugs very quickly. Maybe it gives you different results because your old code had bugs, right? And then that's a good thing to know. And then you can even leave this in here over time for a while, only triggered in debug builds or something just to validate things. Okay, super valuable if you have this test suite. Now we have a test suite. However, and this is the but, and it's a big but, not all our tests pass right now. They should, like, okay, the way our tests work is we record input for each level and we play back the input. And there's actually two kinds of tests. Um, I'm not sure that was a good idea ultimately, but our original tests that I programmed first were untimed. They just say what the keystrokes are, and the playback code like waits for the keystrokes to finish and so forth. But the other kind of test is a timed test because, if an object's like moving out in space and you want to move at a certain time, then to play, you need to play back that event at the right time, at the same time as it did when you input the things, or you won't get the same result, right? So these tests are supposed to deterministically play back. Now, here's the thing. Throughout my entire career, this has always been a problem every time I do it. I've heard other programmers say like John Carmack said one time, like, oh, we did this for inputs and it works great, blah, 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 right? Um, I have literally always had a problem with this technique. It never works right. In fact, even in original Braid, there's a World 5 thing where it does your parallel universe shadow guy, and it uses a technique like this to, we record your input and we play it back. And like that had little bugs where it didn't reproduce exactly. We fixed it a little bit after launch, but in original launch of Braid, it was a little bit flaky in ways that wasn't fair to players. Um, So here, our tests don't always play back correctly. And sometimes, though, that's for legitimate reasons. Sometimes we fix bugs in the gameplay code so the correct result changes, right? Or we change timings in levels, or we change some rule about how certain interactions happen and the correct outcome changes, and then all the tests we recorded break. That's legitimate. But there's also, though, some bugs in the system somewhere. And what these amount to, I think, and we're going to explore this for the rest of tonight. But what these amount to, I think, is just little bits of either non-determinism in the system or the playback code not really understanding what the constraints are on when an event should be input, which seems like it shouldn't be a problem, but I'm just putting that into the universe of discourse here, right? So the problem is, so we have 900 something tests in this game, right? 900 something levels. And if most of them work, so some of the ones that break are really, really long ones. And if a test is really, really long and has many, many sequential steps and something in there is a little bit flaky, it's not that surprising if it doesn't reproduce exactly all the way till the end. So like I sort of have this attitude about that. Like, fine, not all of the tests need to work, but we've definitely had just cases where more things break than we would like slowly over time. And again, it's confusing because maybe that's a bug I just introduced, but I'm also working on the gameplay code all the time. And so maybe the legitimate outcome of an operation changed and all that, right? Okay. The reason I'm saying all this is for this comparative, do the old support stack and the new support stack and make sure they're the same. For that to work, you want your number of test fails to be small or zero. Ideally, it's zero because then all your tests work and it's great, right? But even if it's not zero, if it's like a handful of the biggest, most complicated levels that are known that they don't test correctly, that's fine. But when it's like 111, which is what it was the other day, and maybe you run multiple times and you don't even get the same 111 without making any changes, then you can't use the tests to validate this thing exactly, right? Um, so I mean, well, it's weird. Okay. So you can, the part that compares the arrays and makes sure that the arrays are equal, that could still work. But of course you're inserting this and it's probably not the only change you're making in this code and all that, right? And so to validate that the outcome is correct, not just that some leaf way down in your code is returning the correct result, but that the outcome as the player sees it on the screen is correct. The way that you validate that is through the test suite, right? And if if there's this miasma preventing you from being very clear about that, that's a problem. And so that's the chain of dependencies. Like I woke up today, I started thinking about, hey, it's time to fix some of this gameplay code to not be super slow. That felt really good, that idea. Um, and then I was like, oh yeah, it's going to be hard to test. So we want to investigate why some tests are failing and then try to fix them.